Nice to meet you all. A bit of a short intro about myself. My name is Guy Vinograd. I've been developing software for over 20 years. And in the last 6 years, I've been leading Softimize. Softimize pioneers a new category of Ownable IoT and IoMT platforms. M stands for medical, by the way. Ownable platforms allow developers of IoT solutions and connected medical devices to drastically cut the cost of development and time to market, while, unlike third-party platforms, maintaining full ownership of the intellectual property of the entire solution. So that's what we do at Softimize, and now I'll share my screen to discuss architecting a complete IoT solution. This session is about the angle of developing what does it take to develop an IoT solutions for millions of users and millions of devices. It takes a lot because here we have an architecture that is complex and highly multidisciplinary. And that's why we developed a new methodology to do that. We call it end-to-end IoT architecture. It is much needed because most of the technical guys leading IoT products are not thinking end-to-end yet. They tend to stay in their comfort zone. For example, a hardware guy will start the hardware design first and leave the cloud for later. But actually, no component can be overlooked. What we found out is that a complete architecture should be designed before developing anything, or otherwise, it is almost guaranteed that bad surprises will happen. For example, the hardware guy may design the hardware and the device to do whatever it needs to do and leave the communicating with the cloud to later. And, for example, forget about the encryption needs, maybe knows about encryption, but didn't calculate right and understand the frequency or size of messages, and they end up with a weaker hardware than needed. This is very bad because it means that you have a device that doesn't really function, and it might delay all the launch to the field, or in a worst case, will really ruin the reputation of the company if this device gets out there. So sadly, you know, we're also acquainted of some of those cases. So let's talk about those, how to really do it right, how to prevent those bad surprises. And we have two parts in this session. The main part is a review of the major dilemmas to consider and answer when designing our end-to-end architecture. And the second part will discuss the phase after the architecture, the R&D, and the Softimize solution for efficient development of IoT products. Okay, so dilemma number one, where is my IoT gateway? So let's first define IoT gateway is the component that communicates with the cloud. It's in the field and communicating with the cloud. There are three, let's say, probable usual suspects to place the IoT gateway. The first would be in the sensor itself, a combo of the sensor plus the IoT gateway. Another option would be to have a dedicated device for the IoT gateway, and then usually sensors will communicate with some short-range RF to the gateway, and the gateway will aggregate all the signals and send to the cloud. And the third option is to use the user's mobile phone as the device that communicates usually via Bluetooth Low Energy with a local sensor and transmits its data to the cloud. So these three options have four basic differences: cost, energy consumption, ease of use, and the network availability. And let's see how those differences come to play in various scenarios. Let's start with the first question that is needed to be asked. What is the relation of the sensor and the human that owns it? For example, if this is a sensor that monitors the human, then we can also assume that the mobile phone of the human is near the sensor, because we assume that the mobile phone of us, we carry it with us all the time. So in that case, the probable suspect for the IoT gateway is just a mobile app that is installed on the mobile phone of the user and communicates via some kind of Bluetooth with the device. Why this is the leading option? Mainly because of cost. We don't need to provide this IoT gateway hardware to the user, because he has the phone. We just tell him install an application. So the total cost of our IoT solution is the lowest. For example, companies we work with, such as EarlySense, who develops a sleep sensor that's in the bed of its user, or Heramed, that develops an ultrasound monitor for pregnant women, chose this architecture of device via Bluetooth or BLE to a mobile application, and from there to the cloud. If that's not the case, then we have to go to the other options, or a dedicated gateway, or the combo. The first question we'll ask is how many sensors are in the location of the sensor. Let's say that the answer is there is only one or two sensors there. For example, if in the case of a cloud camera, a home cloud camera, you usually purchase one or two cameras to your home, and they transmit their video to the cloud. The FLIR FX camera is such an example. Then, in this case, it would be best to put the gateway in the sensor itself. Why? Because it's simpler to the user. It's only one device, so the setup of that device to communicate with the cloud is simple. On the other hand, when you choose a solution that involves a gateway, also a dedicated gateway, then you provide your user with two devices, and each of them has to have its own setup, and there is a setup of connecting them to each other, and it makes the system more complex. So for ease of use considerations, the combo device and gateway together works very well. However, if there is a large number of sensors for the given location, then there is a more significant consideration that comes to play, and it is the cost. You probably know that the communication chip of short-range RF, such as BLE, is much cheaper than the communication chip for long-range RF, for example, like 3G or cellular modems. So the differences are a BLE chip might cost even less than $1, and a long-range modem, cellular modem, may cost $5. So let's say you have 100 sensors. If you use the combo alternative, then only for the communication chip, you pay $500 extra. Whereas if you can use a short-range RF that costs $1, then you pay only $100, plus the cost of a dedicated gateway which usually ends up in the area of some tens of dollars. So it's much cheaper, and the more sensors you have, the more sense it makes to have a dedicated gateway. But that's not the only consideration. Another one would be if you have sensor-to-sensor interactions. I mean, two sensors in the same location need to work together. For example, if one sensor detects something, the other sensor or actuator is doing something. In this case, a gateway is important to manage those interactions. Why? Because you may need to mitigate scenarios where the cloud is not available, or when you need a low latency and the latency to the cloud is too high, then this local dedicated gateway might be needed. Another consideration, another question we ask is how easy it is to get physically to the sensor, how easy to maintain it. The main use case here is to exchange a battery or to charge a battery. If the sensor is near us, then no problem. We just hook it to the charger and everything works. But if it's something that is far away, or sometimes it might be example is a parking sensor buried in the sidewalk. So in those cases, it's hard for us to exchange a battery. And in those cases, what we'll need is a solution that is very conservative in energy. And RF sensors, short-range RF, is much cheaper and energy consuming than long-range RF. And that's why in those solutions, also a dedicated gateway would be best, because it enables us to put those low energy consuming chips in the device itself. So after all those questions, we know what kind of IoT gateway we need, and then we move on to the second dilemma. Where is the logic and the data? Where are we going to process everything? Is it going to be on the cloud, or is it going to be on the gateway? There are lots of considerations for here and there, but in general, I argue that the cloud, to process and store data in the cloud, is the ideal way to do it. Why? A few reasons. The first would be protection of IP, of the intellectual property. How come the cloud helps with that? Let's say you have an algorithm, which is this is your unique IP. This is the valuation of the company. It depends on this algorithm. So one way would be to put it on the device, and another would be to put it in the cloud. If you put it in the device, you are vulnerable. Why? Because any hacker can buy your device, put the device in his lab, and attack it until they finally, after 10,000 of tries, they will break it, and they will understand and take your algorithm. However, if you put the algorithm in the cloud, it's different, because we protect it in the cloud. We expect attacks in the cloud, and of course, the hacker can try to attack, but then is at risk, because he doesn't know if he'll be caught or not, and if he gets caught, they go to jail. So they are afraid, and they will not try, 10,000 times until they break us, because they know this is the way to jail. So this intimidation, only this intimidation lowers the chance of the algorithm to be compromised if it's running in the cloud. The second and the related consideration is data privacy. And here we're talking not about the intellectual property of the vendor, but on the data of the user itself. If the algorithm is running in the cloud, it means that the processing is in the cloud. It means that the device itself only knows of the raw signal. And this raw signal has little meaning. And if the hacker takes it, and because he stole the device, he doesn't have much. He needs our algorithm to understand what he got. But if we run and process in the field, then of course he can debug it, or maybe we'll forget that we have some cached file somewhere, and we can use it and steal data of the user. A third reason, it's just much cheaper to process data in the cloud, because data in the cloud is paid by the second. Today, with all the clouds, the major clouds at least, they charge only for the processing time you really use. And compared to the device in the field, you have to design the CPU and the BOM, the bill of material of the device, according to the maximum peak, the maximum power you need the device to be at. And this means that sometimes the device will be processing and will return the investment, but a lot of the time, from our experience, it's more than 90% of the time, the CPU of the device will be zero because it's not really working right now. And actually, this means that you paid a lot for hardware that you don't use. And we see it in real use cases where devices that cost some tens of thousands of dollars and located in hospitals were replaced by devices that cost only a few hundreds of dollars that have a strong cloud behind them. Consideration number 4, high availability and durability. This is, the bread and butter of cloud. In the cloud, you have lots of servers, and if your server is now down, then immediately other servers take the work and do it. And even the user usually doesn't even notice that the server that's handling him changed. And of course, durability. Anything you store in the cloud is backed up in a few places, and even if a full disk is burnt, then other buildings contains copies of the data. In contrast, if you store and process in the device itself, and let's say the device sometimes somehow fell, somehow broke, somehow the disk got corrupted, then all the data is lost. You don't have any kind of backup for that. So that's why cloud is very, very powerful. But we have reality, and reality is that the cloud is far, is there, and we and the device are here, and we need, there is latency to the cloud, there might be communication problems, and the cloud will be offline for us, and there is some limited bandwidth. So in those cases, we still need to consider processing and storing data in the gateway itself. For example, as I said, the cloud can be offline, and sometimes we need the field to operate when the cloud is offline. One example, let's imagine an access control door, a smart access control door, that when I get near the door, there is a camera and the door sees me and then decides, according to my face, if it wants to open or not. Of course, this function must operate when the cloud is offline. I'm sure you can imagine that why. And for that, we have to store some of the images of the faces and some of the logic of the face detection in the gateway itself. Another scenario would be true real-time when we need very low latency. Example can be a pan-tilt zoom camera that's not tracking a robber that gets out of the bank, and you need to have the ability to use a joystick, for example, to move the camera to track this robber that is running in the street. And of course, if you turn the joystick left and only after 5 seconds the camera turns, then our robot will be long gone. If we need the millisecond latency, then gateway is our option. And the bandwidth, of course, sometimes the field generates so much bandwidth that it's not practical, not economic to upload it all to the cloud. And then we recommend to do some pre-processing in the field and move only artifacts to the cloud. Pre-processing, not all the processing, because of all the considerations of intellectual property that I discussed just now. So let's say we got all these considerations and we know which kind of what kind of component processes what. Now what? Now next. Now we ask ourselves about the messages, how they communicate with each other. One question would be, what are those messages? What is their frequency? What is their size? And this question leads to discuss the protocols that are relevant. For example, the messages from the phone to the device. Can BLE be enough for you? Bluetooth Low Energy. Is the BLE bandwidth and the BLE range is okay? Or, for example, from the gateway, from the device to the cloud, are those messages coherent with the upload bandwidth that I have? Then, when we know all of that, we go to ask ourselves, okay, now we need some encryption. Now, this means certain requirements of the processing of the device. And once we know all of that, we can start deriving the bill of material and see that it makes sense for us. But sometimes it doesn't make sense for us, and we need to optimize. So there are a few tools that we use to optimize the messaging flows. One of them, the basic one, let's see what those messages do. Are they really important or not? Or can I change the frequency to be lower? Maybe I can even unite some messages together and conserve some bandwidth. This is the basic stuff and the first questions to ask. And if this solves the problem, we are in a good place. Sometimes it's not enough. And then another option would be to add string compression. Temporal string compression is very powerful with IoT. What does it mean, temporal string compression? The most familiar example is video streaming. You know, standards like H.264 in video. You send one frame and then you only send delta, because the picture doesn't change, and the same goes for any kind of sensor. Imagine a temperature sensor right where I am. So it says that now the temperature is 20 degrees, and in a minute it will say the same and the same and the same, and maybe in half an hour it will say, okay, now it's 19.9 degrees. So of course, sending a delta conserves a lot of bandwidth, and we know of cases that the stream got shrunk by a factor of 40. Another kind of situation that can be solved would be when you send a lot of information, then machine learning can be used to optimize and send much less information and still retain quite the same value. Of course, you need to have a training period to train the system and to learn what are those important metrics. Okay, question number 4 would dive into the protocol. There are a few kinds of protocols that a device can communicate with the cloud. Cloud, internet, everybody thinks automatically about HTTP, but it's not one size fits all. And when you have small packets, small payloads, for example, that temperature sensor that I just mentioned, Then MQTT, a binary protocol, is probably the better solution. You see in the slide, it saves more than a factor of 10 in energy consumption, and the same goes for network bandwidth, and it's something worth looking at. Security is another consideration, because, as you know, to adopt an IoT product, the main barrier that everybody is talking about, that they're afraid that they will enter some kind of spyware into their house or into their workplace, and they must be sure and certain that the solution is secure. Well, security is divided to three main subjects. The first is the one we all think of intuitively. It's to protect from breaches. Of course, this is a full lecture just on best practices. So I'll go to the visible stuff of that. The visible is privacy. Privacy means that the users don't only count on you that you can store the data and you don't lose it, but they can also count on you that you store the data and don't give it to anybody else. Today, with Europe, it's already formalized with the GDPR, Global Data Protection Regulation, which from May 18, 2018, any kind of software vendor and any kind of solution must adhere to. And not only in the EU, in other places in the world, people fear about their privacy, and it should be highly taken care of and also declared in a privacy policy document that you can show your users, and they can read it and really understand it. This is important, and of course, if you can arm yourself with some ISO standards to have some third parties say that you are secured, that would be great. So think about it when you develop your solution. And consideration number 6 would be to think and understand the concept of minimum viable product, MVP. I guess most of you know what I mean by that, to develop this minimal first version that truly provides value to our customers, but doesn't take too much time, so you can get feedback as fast as possible and know that you're in the right direction. So this is true, and software vendors have been following this concept for years. But with IoT, it should be practiced with some care, because there are some features that even in version 1, you don't want to miss. One of them is what I just talked about, security. If you deliver your first version and a hacker breaks into it and publish it, then your reputation is lost even before your company got the chance to show its feathers. So bake it into the solution from day one, from the design and the architecture, and don't take your discounts there. Second thing is logging and analytics, which means that your device should come with functionality that uploads the logs and other events and important stuff to the cloud for further analysis. Because when you have a bug in the field, it's not nice. You don't want to travel to all your devices, to detect and analyze the problem and take the log. You better have it in the cloud, and you better fix your software accordingly. And that brings me to the last thing you need: firmware updates. You need to have the ability to upload your firmware to the cloud and let the cloud distribute it to all your devices. Once you have this functionality, your customer sees a bug, you fix it, and on the day after your customer sees that his device is now working properly, he will love you for that, and it will cost you much less than traveling to the field. So this is about dilemmas, the main concepts, considerations when designing an IoT architecture. And now let's go think about the R&D. You know, we need to pass from architecture, from a Word document to code. So what's the optimal way to develop an IoT system? So what is the IoT system? In general, this is this holy triangle of devices and cloud and applications, mobile, web, voice activation. And of course, all this triangle should have all the security and privacy measures in place. This is our goal. This is what we want to achieve. Now the question is how to achieve it. There are three main categories, those usual suspects. One of them would be do-it-yourself, and the other involve platforms. So let's talk about the do-it-yourself. Let's say I want to do this IoT solution. Surely I need to cook it and to have this, execute this recipe. But do-it-yourself means that I need to find the wood, I need to light the fire, and lots of overhead stuff that today we don't really do. We usually use some other machinery and save a lot of time. So completely doing it yourself is costly, just costly in time and effort. And there are better ways. The better ways are IoT platforms. So if we want to achieve this holy triangle, let's start with a platform that gives a lot of functionality out of the box and save time and money. And then on top of it, code and develop the actual application of our own device. And how to code it? Well, first, if we have the expertise in-house, then do it in-house. You know, this relates to hardware and firmware. This IoT platform can be also a hardware platform. And we take it and then we develop the embedded on top of it. And in the cloud, we develop the cloud application. Of course, what we believe in that if you don't have the core expertise in-house for the cloud, for example, then you should probably use a cloud partner to develop on top of it. Why? The main reason is focus. When you do it, if you try going to stuff to an area that's not in your core, you need to learn about it. And if you're not familiar with IoT and connectivity and security and large scale and SaaS and stuff like that, then you're going to use a lot of your time to learn it. And this time comes at the cost of not doing other stuff, not doing your core technology. And sometimes this is more bad than good. So let's see all those platforms. What kind of platforms are there? There are basically two kinds of platforms. One kind is called PaaS, Platform as a Service, which means a third-party vendor with his platform that you take your device, integrate with that platform, and then they have an API that you can take the data for your applications. There is another kind of platforms. It is called the Ownable platforms. This kind of platform is platform that you deploy your own cloud, and you run your own system. You integrate it with your own devices, and you can also own the code of the platform. So you virtually own all the solution. There are a few characteristics of those ownable platforms, making us believe that they are the only relevant platforms for vendors, for device vendors. Of course, there's a lot of other use cases of IoT, but for vendors, we believe that ownable platforms are the relevant option. Why? First, it is the vendor locking. There are lots of platforms as a service out there, 450 and more. This means that one of them will probably become the Salesforce of platform, the Gorilla one, but the other ones will be gone. And this means that huge integration effort with those platforms will have to repeat itself, will be only a temporary solution. On the contrary, an ownable platform is one that it's yours, you stick with it, and you have no locking to this third-party vendor and dependency. Another consideration is the actual cost of the platform. In an ownable platform scenario, you deploy it on your own cloud account and you only pay to the cloud infrastructure. You know, those big players like Amazon Web Services, AWS, or Microsoft Azure or Google Cloud Platform. And on the other side, those third-party platforms as a service, they have a licensing model, which is at least 10 times more expensive than the infrastructure costs. So you save a lot, especially when you are in large scale, when you're dealing with hundreds of thousands of devices, dealing with millions, then you ask yourself, is it wise to give those millions of dollars to the platforms as a service? Maybe there's a better use for this kind of money. A third reason would be data sharing. Of course, in an ownable platform scenario, the data is yours, it's in your cloud, where in the platform as a service, it's hosted somewhere else, and you have no control and don't really know how this data is protected. Deployment is another factor. Say you sold the devices to a certain country, and that country has a regulation that data cannot go beyond the borders of the country. Then you need a deployment in the country itself. If you're using a platform as a service vendor, then you'll have to ask them, do you have a deployment there? And if not, please deploy them. And of course, it's their priorities, their roadmap to decide whether to do it or not. In an ownable platform scenario, you just deploy it in the data center in that country, problem solved. Intellectual property, in an ownable scenario, you own all the intellectual property of this holy triangle, where in the platform as a service scenario, one of those legs, the cloud leg, is not yours, and sometimes for evaluation of companies, this is important. And the last one, say you have a great algorithm, you now want to put it in the cloud because this is what will make your device kill the market. And now you think how you do it. In an ownable scenario, no problem, you just deploy the algorithm in your platform. And in the platform as a service scenario, you can ask the third-party vendor, can you please put my algorithm in the cloud so we can run it? And of course, priorities and roadmap, they will decide whatever they like to do. So that's why the ownable option is the one that lets a vendor really control everything he needs. And we come to learn that this is very important. Let's talk a bit about Think Building Blocks. This is an ownable platform delivered by Softimize. What's the benefits of Think Building Blocks? So it starts with device components, manage the devices, the databases of the devices, the certificates. You know, each device has its own certificate for the mutual authentication flows. Manage the firmware updates that I briefly discussed earlier, the ability to upload the firmware to the cloud and to distribute to the devices and do some A/B testing and lots of complex logics, configuration management of the devices. Same goes for users, management of large-scale users, millions of users, role-based access, what user is permitted to which device and which kind of function of that device. And also multi-tenancy, the ability to sell devices through channels, integrators, some networks of factories or hospitals, and let those channels manage their own island of devices and users, sub-administration if you like. So Think Building Blocks bring this multi-tenancy to play. The other important packaging is the analytics one. real-time streaming, real-time processing of algorithms. So we get a stream from the device, analyze it, and run algorithms and provide immediate response back to the field within a latency of less than 1 second. Batch analytics to go over large databases and large data sets and provide new insights. Rule engine to allow you to configure upon certain event, certain threshold cost crossed, what action you want to activate and notify the user, send an email, send a REST API call to a third-party SaaS. You see those this cloud in the left side. And workflows, those complex processes where you need to do step 1 and then maybe ask the user to do something and then move to step 2, step 3. This is also part of Think Building Blocks. Another packaging is the monetization. When you want to sell premium services and you want to charge and invoice customers, and then this is the block for that. Another part is the security, of course, the deployment of the platform, the configuration of all those microservices composing the platform, each with the granular permissions of what to do and from where to do it, to pass all the security certifications such as GDPR, HIPAA, etc. Audit service is also part of this package. Another benefit is the integrations layer, the way of the platform and the application on top of the platform to become a platform on its own, to enable your customers to integrate with your IoT solution via the REST API, via the SDKs, and etc. And a very important feature is the scalability of the platform. Think Building Blocks is built for millions and built for optimization and cloud cost optimization that makes it this 10 times lower than other solutions pricing possible. And in addition to that, it is also a multi-cloud platform, which means that even today, maybe today, one cloud is the best, maybe in a year from now, another cloud would be best, and you want to have to be able to move freely between clouds and not be vendor locked in the cloud level as well. So Think Building Blocks is multi-cloud and also cloud native, and this is part of the magic of doing this cost optimization. We have experience with TBB with all sizes of device vendors, starting from those billion-dollar companies to the left. FLIR, for example, is a $5 billion company dealing with IP cameras, cloud cameras, and lots of startups to the right, serious startups, lots of in the medical IoT, Internet of Medical Things vector, which is, exposed to strict regulation, FDA regulation, and the highest possible security measures are applied in this scenario. I'd really like to hear about your IoT challenges. If you can drop me an email, and I'll be happy to talk about it. Thank you. Bye-bye.